All right, so today we are going to continue our discussion of logarithms by showing how we can use logarithms to solve exponential growth and decay problems. All right, so in Math 108, in Chapter 3, you learned a couple of different ways to express exponential growth and decay. All right, you learned that you can express exponential growth and decay with in this form, q equals a times b to the t, where b is the growth factor, and b also can be expressed as 1 plus r, where r is the growth rate. So this is giving the r given in this form of the equation is a percent increase over a certain time interval. Okay, a discrete time interval, one of those discrete time intervals. Okay, so for example, if you have a bank account that's growing at 2% per year, your growth rate would be 0.02, your growth factor would be 1.02. Okay, and every year you would multiply your balance by 1.02. Okay, and you earn interest on that interest, right? So your bank account is going to grow exponentially. Okay. Now, when the growth rate is greater than 0, you have exponential growth. Okay, so the value is increasing over time. If the growth rate is less than 0, you have exponential decay. Okay, so that means it's becoming less over time. The other form, I kind of can think of this as the continuous growth model, although really both of them can be used to express continuous growth. But this form, q equals a times e to the kt, again, a is the initial amount, t is the time, and here the growth factor is actually e to the k power. That's your growth factor. And k is your continuous growth rate. Okay, and the same thing holds for this equation. Here we have k instead of r, but when k is greater than 0, we have exponential growth, and when k is less than 0, we have exponential decay. All right, so the first thing we're going to do, I think, is going to be review for you. Because I think I did some of this in Math 108, but let's kind of review this. Here we just want to convert here this continuous growth model to the form q equals a times 1 plus r to the t. So we're just converting it to the other form, and we want to find the initial value, the growth rate r, and the continuous growth rate k, okay, for this model. Now, in your book, if they don't specify, if they just use the term growth rate or just growth, then they're referring to r. Only when they refer to a continuous growth rate do they mean k. So just keep that in mind. Unless it specifies specifically and a problem uses the word continuous growth rate, assume it's r instead of k. I would prefer that they use like a discrete the term. There's some way to distinguish between r and k rather than growth rate and continuous growth rate. So anyway, but that's just in your book. If they don't say continuous growth rate, assume it's just r, the growth rate. Okay, but anyway, here we're not worried too much about this because we're given an exponential model, and we can just read the continuous growth rate right off of there, right? The continuous growth rate is a negative 0.04. Okay, so we actually have decay in this case. But we want to get, well, actually, why don't I just write down what we know so far. We know a is equal to 6. That's the initial amount. So when t is 0, okay, e to the 0 is 1, so at time t equals 0, the amount, the quantity, is 6. Okay, and we can just read right off from here that k is equal to negative 0.04. Okay, we don't need to do anything. But in order to get the growth rate r, we have to convert this to the other form. Okay, so what we're going to do, well, we know, actually we could say that b is equal to e to the k, right? And if I do that, I get 0.9608. That's what e to the k is. Okay, so if I want to rewrite this in the form q equals a times 1 plus r to the t, I would write q equals 6 times 0.9608 to the t. Okay, and my r value then, okay, so remember r, so the b is equal to 1 plus r. Okay, so in order to get r, I have to subtract 1 from b. Okay, so r is equal to 0.9608 minus 1. Okay, so my r value is minus 0.09. Oops, not 9. Let me get a. I was gonna get the eraser, but all right, let's erase that. All right, go back to the pen. All right, so 0.0392. Okay, notice it's negative again, which makes sense because it's still exponential decay, no matter which form we put it in. Okay, so I'm going to give you a chance to try this one, and you can pause the video, and while you're working, I'll finish it, and you can come back and check. All right, so here's the answer for part B of that example. Here we have exponential growth because the k value is positive. R value is positive as well. But it's really the same process. It's a positive growth rate. Here we have a negative growth rate, which is really a decay rate. So anyway, there you go. Pretty straightforward. Let's go on to the next example. Now in the next example, we are just going to go the other way. We're going to take a model that's in the form a times b to the t and convert it to a times e to the kt. Okay, so we want to convert it, and then we want to also find the initial value a, the growth rate r, and the continuous growth rate k. Okay, so here, okay, we know a is 5, right? Because when t is 0, 1.2 to the 0 is 1, so the initial value is 5. We also know that b is equal to 1.2. Okay, now we're not asked for b, we're asked for r, but we know that r is equal to 1, or b minus 1, right? So r is 0.2. Okay, so we got that already. Now let's convert it to the other form. Now, if you remember back here, let's see, we had b equals e to the k, sorry. And we want to find k. And we know b is 1.2. So how can we get k? Well, the easiest thing to do would just be to take the natural log of both sides. Natural log of b equals the natural log of e to the k. The natural log of e to the k is k. So k is the natural log of b. Okay, so we'll just do that. Let's say k equals the natural log of b, and b is 1.2. So when I do that, what do I get? I got 0.1823. It's a good measure. All right, so if I want to write the model in this a e to the kt form, we have 5e to the 0.18232t. Okay, so that's our model. And these I should point out that these functions are exactly the same. Okay, they will give you, for the same t, they will both give you the same q values. Okay, so these are really the same function because they take the same input and map it to the same output. They're just in a different form. All right, so I'm going to have you try the next one, and I'll come back and show you the answer. All right, there you go. There's the answer for this one. Hopefully you got it. If you have any questions, as always, you can ask me by email or office hours. So let's scroll down here to the next problem. Okay, these are a little different. Okay, it's really the same question though. It's asking for these exponential models, we want to find the initial amount, the growth rate, and the continuous growth rate. But they're not in either one of the forms that that I showed you earlier. Okay, these are well, different. These are different. All right, but we can still find, we can use some algebra to convert these equations into the forms that we had previously. Okay, so either q equals a, let me write this down here, q equals a b to the t, or q equals a e to the kt. Okay, we can do that. We can rearrange this. So let's take a look at what we got here. All right, the first thing I'm seeing, we have an exponent that it's not just t, or it's not kt. It's something different. So let's see if we can work with that first of all. First thing I'm going to do is try to take this exponent and break it up. So what we've really got here is e to the, it's t minus 2 over the whole thing over 5. But I can write that as t over 5 minus 2 over 5. Okay, that's the whole exponent. All right, all I've done is divided both the t and the minus 2 by 5. And now I can use the properties of exponents to write this as 70. Now you can see this e to the t over 5, that has t, but I can actually write this as e to the minus 2/5 times e to the t over 5. Okay, now I've gotten it broken up, and this right now is just a constant, and I could calculate that. I can put that into my calculator. And actually, I might as well put this whole thing into my calculator. 70 times e to the minus 2/5 is a constant. Okay, so if I put that into my calculator, I get 49.9224. E to the t over 5, which I can also write as 0.2t. Okay. All right, so now I've got it in this continuous exponential growth model, and I can read off the initial value and the k value. Okay. But I'm going to take one more step before I list out all of those, because I can write it in this first form. Just by now I know that b is equal to e to the k. All right, so let's calculate e to the k, 9224. If I calculate e to the 0.2 power, I get 1.2214 to the t. Okay, and now, so now I know that a is equal to 49.9224. I know r, well, let's list out k first. That's easy enough. K is 0.2. Okay, and r is equal to b minus 1. So I can just subtract 1 from this 1.2214. So r is 0.2214. Okay? All right, so here's another one for you to try. It's kind of the same process though. So take a look at that and come back and check your work. All right, so take a look at the answer here and see if you got the same thing. So the next thing I want to talk about is just some examples of applications of exponential growth models. And again, we're going to be using logarithms as part of the solution. So in this case, we have a 200 microgram sample of carbon-14. The decay is according to this formula. And so Q is in micrograms, T is in thousands of years. Now that's important, so pay attention to that because that's going to determine what the units of our answer is. And so the question is asking, in how many years will there be 25 micrograms left? Now, just as an aside, I want to let's first of all look at what is the decay rate of this formula. Okay, so we have basically B is equal to 0.886. So that means that R is equal to 0.886 minus 1. Okay, so R is equal to a negative 0.114. Okay, so now what are the units of that decay rate? Okay, now that's in a decimal. We could also say that this, so this is negative growth, which means decay, so positive decay. All right, so we can say that the decay rate is 11.4% per, it's not per year, it's per 1,000 years. So per 1,000 years. Okay, so it's important to note what time unit the t value is in, because that's also going to determine what the units of your decay rate is. Okay, so just be aware of the units. All right, so let's actually answer the question. So we have a function 200 times 0.886 to the t, and we want to know how long is it going to take for the quantity to decay to 25 micrograms. Okay, so we can just set up the equation. We know that at any given point in time, this equation, this formula holds, and we want to know when is that formula going to be 25. All right, so now we just have to solve for t. All right, well, first thing we could do is just divide both sides by 200. So, at least that's what I'm going to do first. That's not necessarily what you have to do first, but that's what I'm going to do first. I'm going to divide both sides by 200. So if I divide 25 by 200, I get 1/8, which is 0.125. Okay. So now I can take the natural log of both sides. Now again, taking the natural log of both sides allows me to get the t out of the exponent position. So if I take the natural log of both sides, I should also mention too, I could take the log base 10 of both sides. It really doesn't matter. I just want to take a log of both sides. Natural log is convenient enough, but I could also get the same answer by just taking the log base 10 of both sides. All right, so if I do that, natural log of 0.886 equals the natural log of 0.125. Okay, so now this natural log of 0.886 is just a number. I want to get t, so I'm just going to divide both sides by the natural log of 0.886. So I get t is equal to the natural log of 0.125 over the natural log of 0.886. I can stick that in my calculator. I get 17.14 17.18. And, okay, remember our t is in thousands of years. So this is 17.18 thousand years. Okay. All right, let's keep going. Next problem. Now, this is an example of, what you're probably going to see. If you have exponential growth, the way you get your exponential growth model is just by just by taking data and seeing if it follows an exponential curve. And we're actually going to talk about more about exponential models in a couple days. But so here we've got annual global carbon emissions from 1900 to 1970. So we have a couple of different points. 534 million metric tons in 1900, 4,053 metric tons in 1970. Assume the growth is exponential. Find the annual growth rate. Okay, so annual growth rate, we want to know what's the growth rate per year. That's going to be R. It doesn't say continuous. So when they're asking for annual growth rate and it doesn't say continuous, you got to assume it's R. Okay, so we want to model this in as Q equals A, B to the T. Okay, now if we take 1900 to be T equals 0, then we know that Q at that time, at T equals 0, is equal to A, B to the 0. Okay, B to the 0 is 1, and we know that at that time there's 534 million metric tons. So I'm going to express Q in million metric tons. Okay, so that's telling us that A is equal to 534 million metric tons. Okay. Now, we also have another point at 70, T equals 70, right? Because 1970, 70 years later, Q of 70 is equal to 534, right? Because that's A, B to the 70th, because that's T. And we know that at that point, we have 4,053 million metric tons. Okay, so we can solve for B. So we would get B to the 70th is equal to 4,053 divided by 534. So that gave me 7.58. 989, for accuracy's sake. So that gives me, I just put that in the calculator, take it to the 1/70th power, I get 1.0294. Okay. And so now I know that my model is Q equals 534 times 1.0294 to the T, giving my R is 0.0294, or I could express it as 2.94%. All right, so nothing new there. We didn't even have to use logarithms, I don't think. So, all right. But the next one, okay, now we want to find the continuous growth rate. So now Q is equal to A e to the kt, right? A is the same, all right? So A is still 534. Actually, we have our model here, so all we have to do is find B. B is equal to the natural log of, sorry, that's backwards. Hang on. Eraser. All right. Let's go back. All right. We want K, right? K is equal to the natural log of B. That's what we found. So the natural log of B, natural log of 1.0294, okay, gives us a K value of 0.02895. Okay, so our continuous growth model looks like Q equals 534 e to the 0.02895 t. Okay. So K is, well, we've already got that. K is 0.0298, but that could also be, we could also express that as 2.895%. Okay, ignore that key. Okay. All right. So let's go on to some other topics here. All right. Another thing that we can look at with exponential models, we could look at doubling time. Okay. So there's a couple examples here with doubling time. So, trying to get this. Okay. All right, so we have a turtle population that is described by this function where t is in years. So, and I assume that p is a population in the number of turtles. So apparently we have an initial size of 175 turtles. We can just read that right off there. Because initially when t equals 0, okay, this 1.145 to the 0 is just 1. So we have 175 turtles initially. Okay. And the next thing we want to find is we want to find the time needed for this turtle population to double. Okay. So we have this p is equal to 175 times 1.145 to the t, and we want to know when is it going to be 2 times its initial size, so 2 times 175. Okay. All right, so we want to solve that for t. Why am I? And so you can notice right away we could divide both sides by 175 and they just cancel. And then we can take the log of both sides, which gives us t natural log of 1.145 equals the natural log of 2. So t is equal to the natural log of 2 over the natural log of 1.145. And I can put that into my calculator and I get, what did I get? 5.12 years. Right? All right. So now we want to know how much time does it take for this population to quadruple? Okay. Well, we have the doubling time. The doubling time is 5.12 years. Okay. So every 5.12 years, it's going to double. So if we want to know when it's going to quadruple, now we could set up the equation and solve it if we wanted to. We could do 175, 1.145 to the t equals 4 times 175. That would be quadruple the initial population. We could solve that. Again, our 175 cancels. So we have t natural log of 1.145 equals the natural log of 4. Oops, 4. And so t is equal to the natural log of 4 over the natural log of 1.145, which gives us 10.24. All right, which makes sense because now after another 5.12 years, our population has doubled again. Okay, so that means it's quadrupled. It's doubled twice. All right, so if we want to know how long it takes for it to increase by a factor of 8, that's just another doubling, right? We are going to go from the quadruple. We're doubling the quadruple size, right? So it will increase by a factor of 8 after another 5.12 years. So the population will increase by a factor of 8 after 15.36 years. Okay, so I just took 10.24, I should write years probably, and added another 5.12, all right, because it's going to double every 5.12 years. Okay. In this problem, we have a population that doubles in size every 20 years, and we want to know the continuous growth rate. Okay, so now this is just, it's kind of working backwards from the other one. The other one we were given a growth rate, or we were given an equation, and we wanted to find the doubling time. Here we're given a doubling time, and we want to find the growth rate. So in order to find the continuous growth rate, now it says continuous, so we have to use the model P0 e to the kt. Kt. That's going to be our population model, okay, so that we can get the continuous growth rate, okay, because that's what it's asking for. So I want to take an initial population, e to the kt, in this case 20, so we have k times 20, because we know that it doubles every 20 years, and I want to know how long, so we know it doubles after 20 years. So if we put in t equals 20, we get twice the initial population. Okay, so we could set it up like that. And then you can see that the initial populations will cancel, right? So I get, if I take the natural log of both sides, I'm going to get 20k, right, equals the natural log of 2. So k is equal to the natural log of 2 over 20, which tells us that the continuous growth rate is 0.03466 per year. Oops, per year. Okay. All right, if we can do doubling time, we can also do half-life. Okay, when we have exponential decay, we have something called half-life, which is the time it takes for the quantity to become half of what it was initially. Okay, so in the first example, we have carbon-14. It decays radioactively at a constant rate of 0.0121 per year. What is the half-life of carbon-14? So when they're asking for half-life, we're just asking how much time does it take for the amount to become half. So we have some quantity A times 1 minus, okay, so it's decaying at this rate. So that means that 1 minus that amount gives us how much is left. So, and be careful because this is in percent. So that means if we convert it from percent, we have 0.00021. This one's really easy to get that messed up because it looks like it's already in decimal form, but this is 0.0121%. Okay, so we convert it to decimal, we have to add a couple zeros there to the t. And we want to know how long does it take until half of that amount is left. All right, so now you can see the initial amount cancels, and we just need to solve this. Okay, so I'll just take the log of both sides, and I don't know, I tend to use natural logs, but you could use a base 10 log, and that would work as well. So if I take the log of both sides, we have t natural log of 0.9998979 equals the natural log of 0.5. So t is equal to the natural log of 0.5 over the natural log of 0.999879. That gives me a half-life of 5,728 years. Okay, so it takes 5,728 years for it to decay to half of its original amount. All right, number 6. Quantity Q of a substance decays according to this formula, where t is in minutes. The half-life of the substance is 11 minutes. what is its k value? Okay, so here we're given the half-life. We're just working backwards. Here we were given a decay rate, and we wanted to find the half-life. Here we're given the half-life, we want to find the decay rate. But it's asking for continuous decay rate, so we want to use the model as they said here, Q0 e to the k, and we know after 11 minutes, so k times 11, okay, so t is in minutes now, so we have to make a note of that. And we know that after 11 minutes, we have half of the initial quantity. Again, the initial quantity cancels, and we can take the natural log of both sides. So 11k is equal to the natural log of 0.5. So k is equal to the natural log of 0.5 over 11. That gives me a decay continuous rate of minus 0.06301 per minute. Okay, so make sure you're clear about that. Because our half-life was in minutes, our decay rate is in minutes. So you have to be careful about that. So this is the growth rate, continuous growth rate. All right, but we would say that the continuous decay rate would be 6.301% per minute if we wanted to express it as percent. Okay. All right. Well, we've gone on for quite a while here. So that's enough, right? What I have is some practice problems for you. I will write out the answers so you can come back and check yourself. All right, so I have the answers here for you, so you can check your work. And let me see, was there something that I wanted to point out to you here? I'll scroll down through here. And again, you can pause if you need to check your answers. Okay, so that's it. So hopefully that made sense to you, and we'll see you again next time.